Hello and welcome back to section 17. In this video we'll go over example 2. Example 2 demonstrates how to solve a problem that has multiple sources that you can't easily combine. So you see here we have a 4e to the negative t and a 2. So we have an exponential function and a constant function. Now you could use our source transformation rules, our equivalent circuit rules, and you could put these together as a single one and write it as 2 plus 4e to the negative t times quantity times u of t, but that really doesn't change the problem. So this is a case where we have a constant function, an exponential function, and then in the future we're also going to have sinusoidals. So we could have three types that we can't easily add together, and if you have different exponents up here, you might not be able to add those up either. So let's go look at this on the visualizer. So I've redrawn it here. I've just called this I1, I2, but these are the same thing. So this is our exponential function over here. This is our constant function 2u of t here. So we're asked to find v of t for t greater than 0. Well, actually, no. We're only asked to find v particular of t for t greater than 0. So that's a little bit easier. We don't have to find the full v of t. So just v particular, so just the steady state response for t greater than 0. So we don't care about the natural response, so we won't include that. So again, basically what we've been asked is say, oh, we have a v of t equal v particular plus v natural, but we're ignoring this part. We're ignoring the natural part. We're just going to zero it out. Basically, we only care about what is this stabilized to at steady state. And if you had to find the full thing, then you would just keep your AES1t in here, or AEST minus delay if they were really going to make it hard, and you could solve it that way. So to solve v particular, we looked at two approaches. One of them is an integration, one of them is a substitution. In both cases, we need to get the differential equation before we can get started. So let's do that. So I have a node v up here. So again, v is defined from this node down to this node. So let's do a KCL at V. Let's note that I have a capacitor, that is I equals C dV dt, and I have a resistor, so that's going to be I equal to V over R. So this is I in equal to I out, so I have I1 plus I2 going in. Again, that's going to be that 2 plus 4e to the negative t quantity ut that we had before. On the way out, we're going to have our current through our resistor. That'll be the voltage V divided by 2 ohms. And we're also going to have the current through this this capacitor. That'll be this C dV over dt. So that's going to be 1/6, and then dV dt. Again, it's a V because this is a V. I want to clean this up, so I want to make this a 1, a coefficient of 1, so my highest order derivative is a first order derivative, so I'm going to multiply by 6. So I'm going to just kind of multiply this and rearrange this at the same time. So I'm going to have dV dt, and then 6 over 2 is 3, so I'm going to have plus 3v, and this is going to be equal to 6i1 plus 6i2. Don't forget to distribute this to the I1 and the I2. And so now, we can, S1 is negative 3, it's right here. And then what I need to know is to solve this for V particular, we're going to look at this when, again, time is greater than 0. So I want to know what my right-hand side looks like. So my right-hand side is 6I1, and I1 is 4e to the negative t, so it is on currently, so I'm just going to write it that way, plus 6 times 2, and again, this is on because I am now at t greater than 0. And so how you handle this, because we can't just, because if you look at this one, S particular is negative 1, and if you look at this one, S particular is 0. They don't match, so I can't put them together. So what you do is you just we're going to use what's called superposition. This is the nice kind of superposition. So what you could do is you could literally redraw this circuit with only I2 and with only I1, solve it and put it all back together. But you don't have to do that. We can just do it with just math without having to redraw the circuit. So if I look at just the case when SP is equal to 1, then I'm going to do my substitution. Again, this -1 does not match this -3, so substitution is okay. So we're going to say that d dt is equal to SP, which is equal to -1, and we're going to bring down our differential equation with our substitution. So we're going to have a -1 v particular, we'll call it prime because we're doing superposition, plus 3 vp prime equal to, and so this is the part that you do have to be careful. So we can't put in both pieces. We only put in this piece because this is caused by this one being on and this one being off. All right. So that's equal to 24 e to the -t. And I should probably leave that at 6 times 4 because what's going to happen, well, actually, no, it's going to be fine. So then you do your math. You get 2 v particular prime equal to 24 e to the -t. V particular prime is 12 e to the -t. Vp prime. All right, so this is 1/2 of our answer. The other half will come from this chain. So we're going to do the same thing. d dt is equal to s particular, which is equal to 0 this time. So same thing, I'm going to bring it down. I'm going to get a 0 v particular. Again, I'm bringing down this differential equation over here. Plus 3 v particular prime equal to just this one. So just the 6 times 2. So the 12. And I find that v particular prime, sorry, this should not be prime, this should be double prime, my mistake. Double prime equal to 12 over 3, which is 4. And then I put these two pieces together. So v particular is v particular prime plus v particular double prime. So that is going to be 12 e to the -t plus 4. All right. And that is 4t equal t greater than 0. All right. Oops, I'm getting my mouth out of the way. So if you have any questions, feel free to reach out.